Okay, so looking today at the whole area of electricity, which it's very hard to predict how substantial this will be in this year's paper because it varies an awful lot, even with the regular paper, where we've got decades of a history to sort of see how much particular items will feature. So in the previous 5 years before last year, before all the COVID complications, electricity varied in its value within the exam paper from 30% to 45%, which is it's a huge variation. It is 30% is very much underrepresenting it in terms of the amount of work that you have to do to prepare this material on the electricity. 30% will be very low. 45% will be a little high. And if you go back over like 10 years, you'll see that it averages out that of the 12 questions usually on the paper, 3 of them are electricity. And of course, how much is that worth to you? It depends on how many of them you would choose to do. And that all those, if you did this, and that would depend, are all exaggerated this year with the increased question choice and the increased number of questions on the paper. So my guess is that it will still be worth something in this region. The balance between section A and section B could change, but I doubt it. Where it'll come up in section B, it doesn't really matter where the question numbers are, it's how many of them there are. And my guess is that there will be something like between 2 and 3 questions on electricity in section B this year. Maybe one of which is at least one of which is likely to mix the electricity up with other parts of the course, like maybe the heat, maybe the modern physics, maybe the mechanics, because that is something that they like to do and have been doing increasingly in recent years. Now, we'll talk about this a little bit more tomorrow, but it is hard to come up with any clear-cut opinions as to who should be preparing, all what do you have this year, 14 questions. Should you be preparing every single part of the course so you can walk in there and that you should be able to answer all 14 questions if you have time to do so, and you're picking your best 6 on the day? It's very, very hard to give honest and clear-cut advice here. I really do believe that those who are looking for the top grades should prepare the entire course because of the unpredictability of the day. If you narrow it down and start leaving things out, you will run the risk that a question that you otherwise love, there could be something on optics, and there's a whole thing on refraction and lenses, and you're all good to go with that, and then it ties in, and there's loads of ways you can tie it in with say a section on electronics and semiconductors, and you've skipped that bit. So therefore that costs you 10-15 marks on the question, and it means you either don't do that question or you take the hit of 3 or 4% to your grade. And if you're looking for H1s and H2s, that'd be a very big cost. If you're looking to just get through this, well then, I'm not going to tell you to be skipping bits, because it's just too easy for me to be blasé about it. What I say is, if you do make choices to skip bits, don't do it haphazardly. So for example, if you decided to leave out some of the electricity, the chances are that the bits you leave out will be there alongside the bits you've chosen to do. So be clinical about it. If you decide to do light, sound, and waves and prepare for it, do every bit of it. Don't decide to then cut any bits and pieces out of that section. If you're doing the mechanics, don't decide, oh, but I don't like simple harmonic motion, I'll skip that bit, maybe it won't come up. Of course, it might not come up, but when you start making those very dodgy decisions of not only leaving things out, but of leaving subsections out, the odds of it going against you on the day begin to mount much more quickly than you would imagine in my experience. If you're looking at the electricity is a huge topic. It does sort of divide into 3. That static electricity, which is basically where there's no electric current, when the charge is not moving in any regular way. is all the stuff about electric charges, contact induction, electric fields, Coulomb's law. Electric circuits is sort of self-explanatory. Everything when there's a flow of current. Capacitance sort of straddles the divide there. That can come up from either perspective. And then the electricity and magnetism and all the different ways that they interact is sort of a separate section. Now, like when I say these are separate, they love intermingling them, but you do tend to get questions that would stake within static electricity or within the electric circuits. Now, whatever else you might choose to skip, and I'm not recommending you do, but if you make hard decisions and that's it, well, you understand what I'm saying. I don't want to be the one telling you to leave bits out. If you're heading to just get out of trouble here, it does make sense to be tactical within the exam. But I would not skip any mandatory experiments, definitions, demonstration experiments. They're the bits that can pick you up marks very quickly, you know, with relatively small amounts of study. And even if you decide I'm not going to answer any long questions on electricity, just a set of short questions, which this year is question 6, which everybody does and usually does quite well on, but they often include definitions. So that's where, if you're cherry picking throughout the course, you're likely to take a hit. But if you're learning your definitions, demonstration experiments, that hit would be reduced. In the mandatory experiments, and I'm going to try to come back to this at the end of the class, the voltage versus current curves are particularly important. Now, we'll work our way back up to all that material. See, I'm just opening up a clock here so I can keep an eye on my time. We'll work our way up to the more advanced, complicated material. One thing you're not going to be asked on the Leaving Cert is this very fundamental and reasonable question: is what the hell is electricity anyway? And the reason you're not going to be asked is that it is by no means a simple question. You've got that we know that if you put 2 electrons side by side, that they will push apart. If you put 2 protons side by side, they will push apart. And we know if you've put a proton anywhere near an electron, they are likely to attract each other. They'll move towards each other. And the force that makes that happen is what we call electricity. And we don't try to get any more basic than that. We don't really try to explain why that happens, even at more advanced levels of study. You come up with sort of mathematical models that might fit in with this, but they never give you a common sense explanation of why the universe has to be this way. We know that with electricity, like charges repel, unlike charges attract, and the 2 types of charge have been labeled as plus and minus for about 150 years. And it's important to remember that it's not, plus and minus does not have any connotation here of value. You know, that if you compare this to you know, money in your bank account, having plus 100 euros is infinitely better than minus 100 euros. You know, plus values are greater than minus values. But when we're talking about positive and negative charge, the plus and minus is just a pretty arbitrary label. We could have gone with black and white charges, up and down charges, anything that just denoted two opposites. You know, and there's no particular reason why it was the proton that had to be positive and the electron negative. A charge of plus 100 coulomb is exactly equivalent in magnitude to minus 100 coulomb. The plus in that sense is not a greater charge than the minus. It is purely a label to denote this idea of like charges and unlike charges. Protons and electrons are not the only charged particles. We'll look a little bit on particle physics tomorrow, and you'll realize, well, be reminded that there are many, many charged particles. But the most common by far within our daily lives are protons and electrons, and almost all the electrical effects that we encounter either with static electricity or with electric circuits are down to the presence of protons or electrons. So they're by far the most important to us. And it's electrons that do most of the work. Protons are buried at the center of the atom inside the nucleus along with the neutrons. And it's very, very hard to add or remove protons from the nucleus of an atom. To do so involves the amount of energy involved in nuclear reactions. Whereas it's relatively easy to add or remove electrons from bodies, because the electrons are on the outside of the atom and much less tightly connected to it. So in general, when something gains a negative charge, it means it's gained electrons. If it ends up with a positive charge, it usually means that it's lost electrons. It's the electrons that jump from one material to another, creating overall electric charges. And the simplest way of doing that is like rubbing, a biro off your sleeve or your hair or whatever it is. Rubbing one material against the non-similar material tends to build up a very small electric charge, and you can sort of see those effects created like that. Well, not lightning, though sometimes you see small sparks, but things like balloons sticking to each other, your hair standing up or attracted to a balloon, picking up small pieces of paper with a biro. All of these are effects that are created with small amounts of electric charge that you would barely feel. If you touch this, you discharge it, but you generally don't feel that effect at all. The charges are so small, but that's all done through contact. That is, rubbing one material off another. Electrons are literally removed from one atom and put onto the surface of another. Now, electric charges, the presence of electric charges can be investigated with electroscopes, which look something like that in reality, but in my cartoon drawing are easier to draw. Look a bit like this: metal bar on top, metal bar down through the middle, and usually modern ones only have one gold leaf. Traditionally they had two. And basically, if there's an overall charge, you see that the leaves stand out. So that if the leaves spread out, it indicates the presence of an electric charge. And that's all you see in using them. They're remarkably unspectacular devices. What is happening, though, in the level that we can see is that if you bring in that plastic bar, let's say it's got a positive charge through contact, it's lost electrons. So then this positive metal or plastic bar up here attracts electrons to the surface, to the cap of the electroscope. So if the electrons are drawn up here, that means that they're gone from down here. So this has now become an area of positive charge. And if the two leaves are both positively charged, like charges repel, so that they stand up. And we can see the presence of the charge through that. If you remove the plastic rod, the charges will redistribute themselves and the leaves collapse again. When it's like that, if you briefly touch the metal cap and then take your finger away before you remove the plastic rod, the charge will last a little while. We say it's permanent, but by permanent, we just mean it survives after you remove the plastic rod. It doesn't survive forever. Right, so the electroscope lets us see the basic effect of the attraction or repulsion of electric charges. Just the fact like charges repel, unlike charges attract, and the various effects of that. That's stuff that ideally you would know from junior cert. How we then analyze the size of those forces of attraction or repulsion comes from Coulomb's law. It states that the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance in between them. Coulomb was sometime in like the mid 1700s. Excuse me. And it usually jumps out at people that there is a similarity, particularly when you write it like that, between this law and Newton's law of gravitation. Newton's law of gravitation says that the force is proportional to m1 by m2 over d squared. Here we say the force is proportional to q1, q2 over d squared, where q represents charge. And there's a really strong belief in physics that that's not a coincidence, that both of these very fundamental charges, two of the most fundamental charges, cannot be following exactly the same mathematical pattern coincidentally. But no one has ever found the connection between them. No one has ever found how these, is there a fundamental force in the universe that both creates electricity and gravitation in ways that we have not yet encountered. Einstein spent the last several decades of his life searching for it. It's known as the grand unified field theory, but like that's what we call the theory. If anyone ever finds it, no one has ever found a way of uniting all the forces, and in particular gravitation, with electricity. So all we know for now is that it does follow a similar mathematical pattern. And the constant, well, unlike gravitation, where we just stick in a g, the universal gravitational constant, the same value anywhere throughout the universe, Here, it's not a perfect constant in the sense that the material in between the two charges, whether it's oil or water or plastic or metal, has an effect. So it's constant for particular materials, but we need different values for different materials, and that's where the value of epsilon comes in. So 1/4 pi, they're constant, but the epsilon is the part that we might need to change its value. Electric fields, the electric field strength is the force per unit charge at a point in the electric field. Basically, that's a way of looking to see what effect an electric charge or an electric field would have on a charge of +1 coulombs if it was there. It's an almost fictitious way. The formula for this, well, E equals F/Q is in your tables. It derives directly from the definition. Force per unit charge, force divided by charge is force per unit charge. But another way of looking at this is that the force in question is Coulomb's law, 1/Q, 1Q, 2/d squared. We're looking at the electric field that would exist in a charge of +1. So you replace one of the Q's with a 1, multiplying by 1, we can only leave it out. So it's Q/d squared. So that version, E equals F/Q, is in the tables. That's the defining formula for electric fields. Whereas this one, 1/4 pi epsilon Q/d squared, is not in the tables. Coulomb's law is, but you might need to use it in this format. Just be aware that you just drop the Q, drop one of the Q's. The unit is newtons per coulomb. Remember, there's no excuse for dropping marks on units in your exam because they are all listed in your table. Starting, I don't have a set of tables beside me here. I think it's around page 40 something. There's all of the units for anything that's going to come up at Leaving Cert or beyond are in there. And every time you leave out a unit in Leaving Cert or get it wrong, you drop 1 mark. So, if you run out of stuff to do in this year's exam, which could happen given the fact that there are such a reduced number of questions with 3 hours to work with, one thing to do would be to hunt through the whole paper and check that you've got all the units right. Now, let's look at how that might come up in a question. So from 2013, question 12C. So define the unit of charge, the coulomb, and state Coulomb's law. Calculate the force of repulsion between two small spheres when they're held 8 centimeters apart in a vacuum. Each sphere has a positive charge of +3 microcoulombs. And copy the diagram above and show on it the electric field generated by the charges. Mark on your diagram a place where the electric field is 0. So define the unit of charge, state Coulomb's law. So Coulomb's law states that the force between 2 point charges is directly proportional to the product of the charges, inversely proportional to the square of the distance in between them. It'll be no harm to stick the formula in with that as well. Very often the formula will get you full marks as long as you explain all the letters. So if you just say F is proportional to Q1, Q2/d squared, you get half marks. If you say where Q represents charge and D exists in between them, you'll probably bump it up to 6. What is the Coulomb? Now, this was a bit of a curveball when it came up in 2013, because as I said before, there is no definitive list of definitions that you can be asked in the exam. It is very much a common sense approach, and usually the exam is very fair, but Coulomb is not a definition that any of the books have, maybe some of them do. And it had never been asked in the past. So caught everyone by surprise. It's a very rare thing. I'm not trying to make anyone paranoid here, but if this does happen, if you're looking for the definition of a unit in the exam and you've never, you don't have a clue what it is, the units follow the formula on which they're based. So for example, we know 1 ampere is 1 coulomb per second. Current is charge divided by time, or charge is current multiplied by time. So the definition of a coulomb is 1 amp flowing for 1 second. It follows directly from the formula on which it's based. Now, that's a bit of a stretch, that's a bit of a reach. You'd have to have looked at the right formula for that to even work for you in the exam. But that's the sort of stuff you can do if you're up against it. But I say I don't want to make you paranoid. Coming up with an unusual definition or unit, or asking something that has never been asked before, is not something that's going to happen on 14 different questions this year. Usually it doesn't happen at all. Generally there's maybe 1 question on a paper every 2 or 3 years. For teachers are thinking, hang on, I never thought that's not on the course, is it? And look, there's no point in arguing about these things. It can seem unfair, but it is a small thing. If it does happen, try to follow the maths, try to follow other things and see if you can figure it out. And then the mathematical section. So we always have formulae in which do we calculate forces or carry out any of the calculations in physics. So if it's a mathematical section, find a formula. Never move on without writing down a formula. If you're stuck, write down 2 or 3, see if you can sub into any of them. It would be unlikely you wouldn't have picked up a few marks at that point. Here it is the obvious Coulomb's law formula. Epsilon 0, if this is in air or vacuum, we refer to it as free space, and that value is on page 46, 47 of the tables, in the middle of the tables. The Q1, Q2, they're both microcoulombs that are 10 to the minus 6. These prefixes, a micro this, a milli that, a lot of them you'll be familiar with just through practice. I'm just flicking through a set of tables I spotted I do have here. Yeah, page 45. They're all listed on page 45. So if you forgot what a micro is, you go to page 45, and then on the right-hand side there, they tell you that a micro can always be replaced by 10 to the power of minus 6. And they have in the last few years brought up 1 or 2 unusual units. So like a pico something, a picocoulomb would be something they could bring up, or a picosecond, or a piconewton. All these prefixes can work with any unit. So just go to page 45, have a look to see what's there. If it's a pico, anything, it'd be 10 to the minus 12. And it doesn't matter that you mightn't be familiar with that in advance. So then write down the formula, sub in, show that on the paper. You don't need to, you can do it all in your calculator. And then write down the answer, 12.64 newtons. I should talk about the marking scheme in a second. Drawing the shape of electric fields, these are all the notes that we'll send out tomorrow, I guess. And they basically, you can practice them by just copying them out of a book or notes, but the logic to them is that the arrows always show what way a positive charge would move. So if you these positive charges like locked in place, if I drop another tiny little positive charge down here, which way would it move? So it'll move away from that plus, but as it moves away from the one on the left, it begins to sense this one on the right, and it gets pushed upwards. So if the logic of their drawing is that the arrows at any point show you what path a positive charge would follow. Now, let's look at the marking scheme there. So if all you did on the mathematical section here was write down 12.64 newtons, they'd probably give you the marks. Like if you don't show all your work and don't explain everything, it's not the end of the world, it's just bad practice. And if if it's obvious that you could only have got this answer through a correct calculation, they would be pretty mean to deny you the marks. But what if you wrote down 1.264? And obviously what's happened, you've tapped some numbers into the calculator incorrectly. At that point, if that's all you've written down, well, everything you've written down is wrong, so you get no marks. Now, the person correcting it might think, oh, I bet you it's just a trivial mistake with the calculator, but it doesn't matter. They can't give you marks on what they imagine you might have been thinking. They have to give you marks for what's on the paper. So if you've written down a formula, then subbed in correctly, and then come up with an incorrect answer, 1.264. Well, they can see you had the formula, you can see you had the substitution. So then the only thing that can have gone wrong is a trivial little mistake with your calculator. And that's usually a mark, like a cost of -1. So by showing the formula, by showing the subbing in, by showing all the work on the paper, not for your own sake, but for the sake of the person correcting it, you are shoring up your mark. You're like often reducing, and there could it be 9 marks down to 1 for any mistake you might have made. But quite honestly, there's a better reason to be rigorous and write down every formula, every substitution, every step of every calculation. It's because when you do that, you're much less likely to make mistakes. Most of the little mistakes we make in maths are for the bits that we do in our head. Now, electric circuits. So the ordinary symbols are all shown here, and this is mainly all that comes up. The switch, when you close the switch, you now have a path from minus to plus. The electrons can now move from minus to plus, and like we saw at FET at the beginning of the class, if you were all logged on at that point, the electrons will now move from minus to plus. But even though we know, we have known for a century or more, that that is what will physically happen inside that circuit, the unfortunate truth is that electrical engineering was quite advanced before we discovered what the electron is in the cathode ray tube, stuff we were talking about yesterday. And for various reasons, prior to that, the assumption had been made within the world of electrical engineering that it's the positive charges that actually move. Now, because it's incorrect in this kind of standard electric circuit. There are situations in liquids and stuff where the positive charges do move. So it wasn't a crazy mistake they were making, but it is very confusing because in most situations now we're looking at it is the minuses that move. And yet if you look at most books, most like animations of these, they'll show it as positive charges moving from plus to minus. And it's just confusing. That's conventional current, where we show it as if the positive charge is moved, and it's probably easiest to go with that and just keep in the back of your mind that in fact most of the movement is in the opposite direction, minus to plus. So the key measurements are voltage, which drives the current in quotation marks. More specifically speaking, voltage is the energy per coulomb. It's the energy that the electrons are given by the battery or the power supply. But I always picture it as the voltage pushing the charge out, and it's never done me wrong to picture it like that. Resistance is what restricts the current, slows the current down, stops the electrons from moving so fast. If you see a narrow across a rectangle, that's a variable resistor where you can change the resistance, usually by sliding something along the top or alongside the resistor. And electric current is usually represented by the letter I, and they're all interlinked by the formula V equals IR. So I is the movement of the charges, the electrons, R is what slows them down, voltage is what drives them. And this formula, which comes from Ohm's law, is sort of the default formula if you're looking at electric circuits. Now, a lot of the study of electric circuits that we do in detail is based on resistance. Like we could look at batteries in detail. We could look at battery design in detail. We could look at how electrons move from one atom to another inside a metal, and like that's barely mentioned in the syllabus and is never asked about. One thing we do go into some detail on in the syllabus about electric circuits is resistance. So in a common sense understanding of what resistance is doing, it slows down the movement of electrons and therefore reduces the current. But the actual definition for this comes from Ohm's law, which is resistance of an object is the ratio of voltage applied across the to the current which flows through it. So resistance is voltage divided by current. Now, if we have resistors in series or parallel, so series often drawn like as one straight line, but what it strictly speaking means is that the same current flows through the three resistors. It doesn't matter what way they're geometrically arranged. And to get the total resistance there, you add up the individual resistances. If they're in parallel, again, that doesn't have to mean they're geometrically parallel. It means that the current has to choose between different resistors and how they're physically aligned. Doesn't matter if they're parallel or at 90 degrees or at various angles to each other. In any electric circuit, they're often, at contorted angles to each other. But it would always be drawn like this, that literally parallel, just to keep the drawings simple. So in that situation, the total resistance follows the 1 over R pattern. 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 and so on for however many resistors there are. Now, the derivations of those are exactly the sort of stuff that could shore up your mark if you're looking for the top marks or get you out of trouble if you're looking at scraping through. And learning derivations is a chore. but these are very, very short. Here, like the total drop in energy or potential from A to B is the energy dropped across first, second, and third resistors. So the energy dropped here is V1, potential energy dropped here is V2, potential dropped here is V3. So the total drop is V1 plus V2 plus V3. V equals IR. So IR total is IR1 plus IR2 plus IR3, but it's the same current through them all. So you divide across by I using that formula. You don't even need a diagram usually. Those 2 lines of working out, and you'd pick up either 9 or 12 marks. There's a similar one for resistors in parallel. The total current is I1 plus I2 plus I3. Each one of those is V divided by R1, R2, R3, and then you divide across by V. Look, I'm running through them very quickly there. They can be difficult to fully understand, but they're not difficult to learn mathematically because it's only 2 lines. Let's have a look at 2005 question 9. Now, this is the difficult part of the question. Remember, at the beginning, there's laws, there's definitions, demonstration experiments. That all picked up something like 30 marks in this question. So those are the easy bits. Those are the straightforward bits that you should definitely prepare for first. But you will have to face some sort of mathematical problem with these. So first of all, what is the total resistance of this circuit? So here you can see it's not a straightforward arrangement where they're all in a straight line or all parallel to each other. So it's a mix of the two. So the current at this point here, so if we see current leaving the battery, reaching this point, it now splits between the 750 and this resistor, which for this part of the question was 500 ohms. So it's choosing between 750 and 500 ohms. So if the current is choosing, that's a parallel system. So we use the 1/R formula to find that the resistance of the 500 and 750 together is 300. You could replace those two with a single 300 ohm resistor. And then the current that goes through this combination of 300 ohms then also goes through this resistor of 300 ohms. So the total resistance is 600 ohms. Now, we know the total resistance at this point, and we know that the total voltage in the circuit is 6 volts. So when we're asked for the current, now we're asked for the current specifically through this resistor. Now the total current that leaves the battery splits at that point before recombining here. So the current going through this 300 ohm resistor down at the bottom is the total current. The current leaving or coming into the battery is the total current, but the current going through the 750 is less than the total current. But to get it, we first of all get the total current. So if it's 6 volts for the whole circuit, 600 ohms for the whole circuit, then there is 0.01 amps flowing in that whole circuit. How does it then split? Well, let's have a look at what happens at this point up here where the current has to choose between the 750 and the 500. You could redraw it like this. The current doesn't care about the geometry, it's just picking higher or lower resistance. Current will take every path available to it. At junior cert, you might have been told the current will take the easiest path. It's a bit simplified. Current will always take every path, but the bigger current will take the lower resistance. So when the 0.01 amps flows here to this point, most of it is going to go through the lower resistance 500 ohm resistor and a smaller amount through the 750. How do you decide or calculate which you're looking for, the 750 ohm current? Well, 500 and 750, they're the resistors. They're in the ratio 2 to 3. And the currents will go in the exact opposite ratio of 3 to 2. So if you remember from ratios, if there's 3 and 2 section or divisions or slices of the total current, that means 3/5 and 2/5. So the 500 ohm resistor will get 3/5 of the current, but we want this one over here, the 750 ohms, that will get 2/5 of your current, is 0.004 amps, 2/5 of 0.01. Now, these are difficult, or rather I should say, they're difficult to learn and prepare for it, given that you can't realistically spend weeks on these. I promise you, if you learned nothing but how to look at the way the current divided itself up as it went through a circuit, you'd nail this totally by the summer and could deal with much more complicated situations than the one I'm looking at here. But that would be a crazy thing to do because you'd be ignoring so much else. So given the time you can realistically put into it, these tend to be challenging, and we know that from how well or how not well they're answered in the exam. But for that reason, they have not been making it more difficult over the years. They have not been looking for ways of, ramping up the complexity of this. They've just been, every few years, they ramp out similar question. And if you make sure you get the idea, any resistors in series and parallel, use the appropriate formula. If there's any relationship between voltage and current, V equals IR, that's going to be the core of it. And if you're looking at a current splitting, work in terms of ratios. And anything close to the correct method is going to be picking you up marks, as long as you're showing the formula, showing you're subbing in. Another question about resistance relates to resistivity. So from 2011, so a list of factors that affect the heat produced in a current conductor, and then a mathematical section down here. So the factors that affect the heat produced in a current carrying conductor, I mean, it's sort of obviously the current. But that's not something you're likely to have learned of. So of all that I've shown on the screen there explaining this, the only bit that you really need to do is the bit down the bottom. It's affected by current, resistance, and time. So if a current flows for half a second, the wire heats up less than if the current flows for 10 seconds. Time matters. The size of the current matters. And the higher the resistance, the greater the tendency is for heat to build up. The maximum resistance per meter of the wire, well, look at the numbers you have. You have a current and you have the power, the rate at which heat is produced in the wire. So that's 2.7 watts. Now, the resistance per meter of length is what you're looking for. And the thing, I didn't introduce this here now, but this relates to Joule's law, which is the rate at which energy is converted from one form to another in an electric circuit. So P is equal to Ri squared. That means that R is P divided by I squared, which is 6. Now you know P, the power, the energy per second, 2.7 joules per second, or 2.7 watts, divided by 20 squared, so that's 6.75 by 10 to the minus 3. And then for a circular wire, we're looking for the minimum diameter. So we can say that the resistance is resistivity by length over area from your tables. The area, therefore, is resistivity length divided by resistance. You're just subbing into a formula, which is in your tables. The only trick to this here is we have to work out, once we know the area, we then go back into A equals pi r squared to work our way down to the resistance and the diameter. Now, I'm showing that up there and I've gone through it very quickly. So if you're struggling to keep up with me there, don't worry about it. The main reason I wanted to put it up was to have a look at the marking scheme for this question, which would be typical of most questions. There's a lot of stuff going on there. There's a lot of maths. Even in the marking scheme, sometimes, they don't have to do all the laborious step-by-step work. They know how, right? But each line there, you can see there's 1, 2, 3, 4, 5, 6, 7, like 8 lines of algebra in that question. But formulae account for 3 of those lines. So if you had any combination, now there'd be variations on how you could approach this. P equals V by I could also work with an extra step. So P is equal to Ri squared. Just writing that down got you 3 marks. And subbing in got you another 3 marks. Resistivity is resistance by area over length. Got you 3 marks. And that one I've obscured it there a little bit. But basically, the only difference between here and here is introducing the area, the idea of A equals pi r squared. So you could interlink it there or do it as a separate calculation. Either one is good. Every formula is picking up 3 marks. Make any attempt to validly sub into that formula and you could easily have bumped it up to 6. So sometimes, being too purist about things can work against you. It's wonderful if you can nail down all the work in and fully understand what we're doing and deal with complicated stuff. Of course, that's wonderful. And of course, you should get top marks. But don't be afraid to stumble through a question. If you can work through a question where you've written down formula then use the variables that are listed in the question. So if you have anything, here you got power and you got current. If you can find a formula with P and I, power and current in it, it's almost certain that that's a relevant formula. It mightn't be the one that crops up in the marking scheme. It mightn't be the easiest way of doing it, but if it's a valid way of doing it, you get marks for every formula you will write down. Always try to push it one step further and sub in to any formula you've written down, because if they feel you're listing 50 formulae, you don't get the marks. By subbing in, you show that you understand what you're doing here to some extent, even if you can't finish the question. Now, capacitance. Now, there's an important thing about question choice in general. I want to use this question as an example of it. So define potential difference in capacitance. A capacitor stores energy. Describe an experiment to demonstrate that a capacitor stores energy. So that's 26 marks there. Then a whole paragraph about defibrillators. I always struggle to say that word. During a heart attack, the chambers of the heart fail to pump blood because their muscle fibers contract and relax randomly. The beating of the heart has gone arrhythmic. To save the victim, the heart muscle must be shocked to re-establish its normal rhythm. A defibrillator is used to shock the heart muscle. Now, there's no mention of defibrillators in the syllabus that you should have learned and understood the relationship to capacitance and, to be ready for this whole question about heart attacks. That's not something that we've been told to prepare our students for. It might come up, in conversation if it ever occurred to a teacher, but equally it might well not. But don't let that sort of awkward paragraph giving you technical background put you off in a question, because in terms of working your way through the exam, that bit just doesn't matter. Let's work our way through this question top to bottom. So first of all, potential difference in capacitance. You might not know them straight away right now, but you'd be crazy if you aren't planning on learning your definitions before the summer. And that's 12 marks straight away, which this year would be worth 3%. I mean, my guess is that it's going to be worth 17, 18, 19% this year for knowing your definitions. Describe an experiment to demonstrate that a capacitor can store energy. In the notes I sent out on last week, and these are also built into the notes I'll send out this week for the electricity. We have all the likely demonstration experiments, which particularly crop up in electricity. So here you basically charge up a capacitor and then connect both ends to a bulb, and the bulb flashes, showing that there's light energy there. It must have come from the capacitor, so the capacitor was storing energy. That wasn't 12 marks, that was 14, I think, in this occasion. Yeah, so I'm underselling it there. That was worth 14 marks. So that's 26 marks, which this year would be in advance of 6% of your total grade nailed down already. So already, this question isn't a disaster for most people. Now, so demonstration experiments, particularly for electricity, are like a real way of getting out of trouble. But what would, even if you were well prepared, hopefully you'd notice the 12 and the 14. So you think, oh yeah, I can get those. But I don't know anything about defibrillators. But the thing is, that bit does not matter at all within the context of the exam. It's interesting, and they're often put in so that in subsequent years, when people are using past papers, they learn a little bit about defibrillators. So they're put in there with a view to being used in future classrooms. But in terms of the exam, everything you need to know is in here. The question is obviously about capacitance. So you turn to page 60, 61 of the tables, and you find a formula about capacitors. And you're asked for the charge stored in each capacitor. So that is C equals Q over V. Charge is what we're looking for, so we need C and V, and they are both given to you directly in the maths. 64 microfarads, 2,500 volts. So 0.16 coulombs. You don't need to have read anything about defibrillators to get that. Don't let those little technical details, background diagrams that throw in there to give the question context, don't let them intimidate you. The energy stored, well, page 61, I think. I'll check now that I've put it out there. no, 62. Down at the bottom, there's a formula labeled energy stored in a capacitor. W energy here corresponds at work, half CV squared. And again, you have both of those numbers directly from the tables. So really, it's only when you get down to the last two parts of the question that you'd have to drift away from just opening up the tables on the electricity section and subbing numbers directly into them. And at that point, for most people, this is already a decent question, even if it's only your last question. But very few people did this question when it came up in 09. Like almost nobody. It was the least popular question on the paper. And why? Well, you know, that included lots of people who were obviously well prepared because they answered other questions well. So they would obviously have been able to get the 20, or most of them would have been able to get the 26 marks here. And if they just open up their tables and plug numbers into formula, they would have been able to get most of the 30 marks down here. So why weren't they doing the question? Well, of course, I can only guess, but I fully believe it's down to being intimidated by this defibrillator stuff in the middle. I understand the intimidation, but you should not allow yourself to be drawn into that. By way of contrast, 1 year before that, this question was on the paper and almost everybody answered it. Now, this is obviously from optics. I'm not going to go into the physics of it right now, but it's really difficult. It includes some maths in here. There's a way of playing around with the 1 over U, 1 over V, 1 over F formula that and the power of lenses that, you know, it's tricky. And it's not something that anyone would have done prior because it's not an example that they'll have likely seen in a textbook. So definitions, sure, but this bit here is quite a tricky part mathematically. And then, you know, generally they're very good at writing questions, but this bit down the bottom is very unclear. It's very, like, reading it at the time, I was thinking, I'm not sure what they're asking me for there. I think I know the physics, but I'm not quite sure what the question is within all of this. And if I do understand it, they seem to be repeating themselves. It was a badly structured question, but everyone did it. Now, why would that be? And didn't do well. So I think it's about comfort zone. So this is, forget about the electricity for a minute. This is about how you pick your questions in the exam. And do not get sucked in to the big mistake of just picking questions on a vague sense of comfort zone. Most students sort of like optics. They sort of like the idea of lenses and, you know, the eye. They can understand all that reasonably solidly because, you know, we have eyes, we've seen lenses, you've done the experiments in this, you did it early in 5th year, you've had loads of time to get used to the ideas very often. So it's, people feel comfortable with this material. So they do, oh yeah, that stuff, like it, jump in and do the question. Whereas capacitors, very often done in 6th year, and it includes a whole awkward bit about defibrillators that you won't have read at all, saying, oh, I don't know what's going on there, so avoid it. But people thinking like that are not going through the question and adding up how many marks they're likely to get for that question. Anyone reading this question for more than 30 seconds should have been thinking, well, I'm okay talking about lenses, but I'm not sure what's going on here, and I don't even know what they're asking me down here. I realize that adds up, those two sections alone add up to 32 marks that are awkward at the very best. So when you're picking your question, when you're reading through the exam, I think this is going to be really important this year. It's really important that you, beside each question, give yourself an estimate of how many marks you'd be confident from that question. And then do the questions with the bigger numbers beside them where you can score highest, not the questions where you just feel sort of comfortable. Okay, we just got a few minutes left. I just want to
throw a question in there to you.
Yeah, sure, Finn, yeah.
Just someone asked, it was, I think it might have been a few questions ago, it was about the, can you go through the ampere definition? I don't know if I'm pronouncing that right, A-M-P-E or E.
I'll note that down. We'll talk about it tomorrow, but basically, I wouldn't worry about it because the definition of the ampere, like, changed officially through university, like there's a university body internationally that agrees these things, and they've been working on this for like 20 years, and they finally last year changed the definition of the ampere. So the new definition isn't on the syllabus, but the old definition is now like wrong physics. So there's no way it'll come up as in state this definition. But I'll note it down and we'll talk a little bit about the fundamental constants tomorrow.
Perfect. And just a quick note to everybody that doesn't know, I'll be sending out the notes again for classes 4, 5, and 6 on Friday. And if you didn't get the notes and recordings for classes 1, 2, and 3, please just shoot me an email and I'll pop my email in the chat function now.
Okay. Now, so we've only got, is there any more questions actually when we're on it? We might as well.
No, it was just the one and then a question about notes.
Yeah, right. So electromagnetic induction is a huge area, and it's a really interesting area, but it is the optional material. So everyone is supposed to study the core material, which is 90% of the course or more. You can then choose optional material of doing an extra little bit about modern physics, which is the particle physics, or an extra bit on electricity, which is the applied electricity, which basically takes this area of electricity and magnetism and goes into more detail on it. So the electricity and magnetism is quite challenging material, but what comes up in the core questions is not. So basically be aware of the demonstration experiments and your definitions for these, and like they nearly always come up and often no more than that. So for electromagnetic induction, when there's a magnetic field passing through a coil, changes of voltage is induced in the coil. And that's electromagnetic induction. Faraday's law basically tells you that the faster the magnetic field passing through the coil changes, the bigger the voltage induced. It happens because inside every coil of the wire over here, every electron is essentially a little magnet of itself. A spinning electron, and all electrons are spinning, are magnetic. So when you move this big magnet, you make all these small magnets move, the electrons. And that's making electric charge move, means you have a voltage, means you have an electric current. The basic formula of this is it's the change in flux divided by time, multiplied by the number of turns in the wire. Flux is a complicated definition. They're all worth learning. But this is an area where it's really important you don't get too intimidated by it, because even though if you're answering questions in this material, you have to know that, oh my God, there's so much here that I barely understand. If you're not thinking like that, you're probably not taking it seriously. But don't avoid material based on all the things you don't understand there. When you decide an exam is, do I answer this question if I can answer the specific question I'm being asked, which is usually much narrower. So we got electromagnetic induction of Faraday's law, and Lenz's law is about the direction of the induced current. So basically the current will flow through a coil, which creates a magnetic field which opposes the change. So as a north pole approaches, the current here flows, creates an electromagnet that tries to push it away. When the north pole is moving away, it tries to pull it back. And you should know same Faraday's law and a demonstration experiment for each. We'll just have a quick look at a question on that before we finish up. So state Faraday's law of electromagnetic induction, 6 marks, straightforward. Describe an experiment to demonstrate Faraday's law. Well, that's the one that was in the applet there. Like that's what you're seeing there is a demonstration of Faraday's law. And in a hollow copper pipe and hollow glass tube with identical dimensions are arranged as shown. Student measured the time it took a strong magnet to fall through each. It took much longer to fall through the copper pipe. Why? Now, copper is a non-magnetic material. You cannot stick a magnet to copper or copper to a magnet. The copper will not respond to the magnet. Only basically materials made from iron, nickel, and cobalt will. Most magnets are steel or nickel, but certainly not copper. So it's not because the magnet is sticking to the copper in the ordinary sense. So we got your definitions, your demonstration experiments. Yeah. What's happening here is that as the magnet falls down through the copper, the magnetic induction occurs. It creates small electric currents in the copper pipe, which creates a magnetic force that tries to hold the magnet up. So copper isn't normally magnetic, but as the magnet falls down through it, it turns it into a little electromagnet. It's never enough to keep the magnet up there, but it's always enough to slow it down. Same thing can't happen with the glass because you can't get any little electric current and you can't get an electromagnet out of glass. Now, last thing, we don't have time to look at this, obviously, but voltage current curves come up over and over again, mainly in section A, the mandatory experiment section. But when it comes out, Ohm's law, we talked about earlier, V is proportional to I. So voltage proportional to current means a straight line through the arc. That's coming from Ohm's law that states for a metallic material at constant temperature, the current will be proportional to the voltage. Whenever two measurements are proportional, you always get a straight line current, a straight line graph when you put them together. But note the exceptions here. That's only true for metallic materials at constant temperature. So it's not much of a law when you have that number of exceptions. How do you analyze when something is following Ohm's law or not? Well, you just create an electric current. You need an ammeter and a voltmeter. Ammeters are always part of the circuit. So whatever flows through our metal resistor down here must flow through the ammeter. And a voltmeter tells us what current is being pushed through that resistor. So ramp up the voltage, measure the current, take several points and draw a graph. This is the single most repeated question in the exam. It doesn't have to be for a metallic conductor. They might ask for a filament bulb, which gets warmer and therefore it doesn't follow Ohm's law. The current levels off. They might ask it for ionic solution, copper sulfate or salt, where the copper and sulfate separate out in the liquid and carry the current. It could be for a gas, which is like a fluorescent light bulb. And again, graph levels off. It could be for a vacuum, which is like a cathode ray tube. And again, the graph levels off. The experimental section alone just deals with metal, bulb, diode, and ionic solution. And that's like, it's a very narrow piece of study. It's a difficult experiment to do. It's difficult to get all the bits working and stuff like that, but they're not asking you to do the experiment. And these are graphs that are really easy to draw because it's not like Boyle's law where you have to remember that it's 1 over V and not V. It's not like frequency of a stretched string where you have to get the square root of the tension of the string to graph that. Here, they're giving you values for voltage and current and just asking you to put dots in a piece of paper and join the dots to get either your straight line or your curve. If you can draw a basic circuit diagram for each of those, and you've just practiced 1 or 2 of the graphs, it's, you know, it tends to be a great question. And like is true for electricity in general, the electricity questions in section A have been getting easier and easier over the years, and people are still avoiding them. And they've been looking constantly for ways of challenging you on the mechanics and optics experiments because everyone likes to answer those. But yet people keep answering them even when they're being getting trickier. So I promise you that if you practice a few question 4s, which in the notes we sent out on last week, you had this document, which is like breaking up the last 10 years up to 2019, topic by topic. So if you just work through those, that'd take about 3 hours. If you get 5 or 6 of them done, you probably have most of the benefit. Take you about 2 hours. And that's worth 10%. This year, 13%. Just to have nailed down those electricity experiments. And don't worry about the fact that you may not have done them. If you can answer the, obviously that's better if you have, but if you can answer the questions that have come up in the past, you're very likely to be able to answer the one this year. And in section B, you can see it jumps around. I can't tell you it's always question 8, but it often is. It's not always question 11, but it often is. But if you go through, that tells you each year where the electricity came up. There'll be about 6 to 7 hours work of hard work plowing through all of those. But if you did that, you would have your electricity questions utterly nailed down. And you would have a choice of those questions this year. Most of the benefit would be gained by the time you get through about 6 papers. So, I mean, depending on how well prepared you are now, how much of the course you have still to do, obviously I'm not giving you work, I'm going to be checking you on it. But that basically work is every exam should be prepared for by working through past papers. And I would strongly argue, and we'll talk about this tomorrow with a bit more sort of study of how you would organize your study between now and the summer, work from past papers and do it topic by topic. But we will revisit that tomorrow. We're going to look a little bit about heat particle physics. I'll stick in a bit about the constants that you might be asked about, the ampere. I'll explain a little bit more about that one. And we'll do that tomorrow in our last class, and we'll send out all the notes and back this up.